hometown. Funny how this all looks different, but it feels the same. Like how life never stops changing. That I get, I see it. Thanksgiving.
Oh, right. So you heard a song, the Thanksgiving song. So this morning I was thinking about what a song to play, and I just realized that, yeah, it's clear that we have a Christmas song. Well, we have a lot of Christmas song, but not sure if we have a Thanksgiving song. So I just found there is a new release for this October for this song. But it's kind of ironic because a lot of things that the song described, like, okay, meeting with family, fill the house with family, it's actually not permitted right now because if you look at the the restriction released by the governor is actually like we are not permitted to have a gathering for more than 6 people. So but the only exception is that, well, if you have a funeral service, then you can have up to 30 people. So some people saying that, hey, let's treat the Thanksgiving as the funeral service of a turkey, then we can get 30 people in a house. Well, that's definitely an interesting workaround, and I don't think that's a good idea at all. So I would probably just have a dinner with less than 6 people to follow the restriction. However, and you should also do the same. But most important thing is that, well, it's still in a quarter, so I'm so glad that we still have so many people in the lecture today, because I remember the first time I lectured on a Wednesday right before Thanksgiving. I only have 2 in my classroom. So, but the awkward thing is that even though you have 2, you still have to lecture. And some people is persuading me that, well, at least you have 2. I have nobody, right? So I'm so glad that we still have a lot of you today, and probably that's the benefit that we also have an online session right now. So today we are going to continue the discussion on dynamic instruction scheduling, and today we are going to discuss 2 of the most important techniques for dynamic instruction scheduling. So it's definitely a good thing that you are in a lecture today, because this is probably the most important lecture for this part of the topic. So before we start, it's always good to set the stage talking about why we are here. So we talk about that, well, all the processors are now pipeline. However, in pipeline design, there are still hazards preventing us to make better progress of our instruction. So if you want to deal with the hazards, then stall is definitely a good approach that easy to implement and address everything. However, as you can see from the word stall, right, it means idling, it means waiting. So it's going to hurt your performance, right? So to achieve better performance for structural hazard, we try to modify the hardware design. For control hazard, we do no matter static prediction that you have been practicing in your homework, or dynamic prediction that, in addition to homework, you also see like the latest advance in branch prediction, for example, the neural network predictors, right? And or say perceptrons, right? So now let's move to another type of hazards called data hazard. And we have been talking about data forwarding. And at the end of the last lecture, we went through Tomasulo algorithm very fast, but because this is so complex, I don't believe anyone really get into the idea of the Tomasulo algorithm. So today I'm going to start with that again. But before we start, right? So remember the reason in theory, right? This is how we can start executing an instruction. So if you want to start executing an instruction, the basic idea is that whenever the instruction is decoded, whenever the inputs are ready, meaning that all the data dependencies are resolved, and whenever the target functional unit is available, there's no reason why you should let the instruction go ahead, right? So for example, if the student has done all his jobs that he needs to be done for his degree, if the student is able to find a job position, if the student has all the withholds addressed, right? There is no reason why we should let a student graduate to make progress for his next stage of life, right? So the same thing, right? The same thing for instructions. So we want to schedule instruction based on data dependencies. And if you draw the data dependency graph for this sequence of dynamic instructions, you will find out the instruction 1 to 3 and instruction 4 to 10, they are actually depending on, they are actually on 2 separate trees, which means that they don't have any, these 2 groups of instructions, they don't have any dependency. However, if you try to reorder them, you will figure out that, well, for instruction 1 and 4, 4 and 3, well, professor told me that in 6 and 2, 7 and 3, they are not in the same tree, right? And same thing for 6 and 1, 7 and 2. are not in the same tree. However, how come I cannot reorder them? Because we are still limited by false dependencies, meaning that it's not true dependency. It has a data dependency just because you are trying to reorder them. And the other thing is because they share the same register. So the key is that you want to reorder them without destroying the correctness of your program. Then the key is because they share the same output register. So you have to the same register for one of their output or input. So you have to figure out if there is a way we can decouple that chain. So a lot of you were thinking about why we cannot just address this by compilers, right? So if you look at what the compilers can do, right? This is what a compiler can see, right? When you translate the C code into instructions, this is what a compiler can see. Compiler can only see, well, there's a loop there. However, compiler has no idea how many times the loop will be executed, right? So this compiled instruction sequence is called static instruction, meaning that these instructions, they are what we stored in the memory or what we stored in a secondary storage. So and without the context of the register value, there's no way we could know how many times the loop will be executed, right? So in this way, right, you cannot optimize the real dynamic instructions. So for example, if you look at the dynamic instructions like this, you will figure out there are chances that, well, we can potentially reorder 3 and 5 or 4 and 5. However, compiler cannot predict that because compiler has no way to make perfect prediction. And even though we make predictions, there's no, the overhead of canceling the execution of an instruction would be huge from a compiler's perspective. And the second thing is that we didn't talk about that much, but you should be aware as well that, well, compiler cannot predict cache misses. So if there is a saying that if the load instruction has a cache misses, right? So you should try to find a way to cover that latency. However, compiler cannot predict that. So and the other thing is that we talk about false dependency. Compiler we say the source of false dependency is because we have limited number of registers. So instructions has to reuse the same registers for input and outputs. So for example, like in this instruction sequence, you can easily tell that there's no true dependency between the first and the second instruction. However, compiler don't know how to reorder them because the compiler only knows is that if we try to do that, then it will cause issues, right? So, and the other thing, which in our example in the last lecture, we also told you that if we try to add the pipeline stage, or if we try to modify the pipeline design, then the compiler optimization may not be working. So we have to address the reordering or optimization through dynamic execution, dynamic out of order execution. So the dynamic out of order execution, because it's in a processor, it has the branch predictor, so we can predict what's going on in the future, and because the processor can build its own logic to flush incorrectly fetched instruction, so we could potentially make that happen. So one of the approach that has been that was proposed in the early days is called Tomasulo algorithm. So the basic idea of Tomasulo algorithm is that it allocates a reservation station for a decoded instruction. And what a reservation station is storing is actually where in hardware is going to generate the outcome for this instruction and what the outcome of this instruction. And for other instructions that depending on the output of that reservation station will be pointing to that reservation station instead of its original register name. So in this way, this mechanism is actually try to redirect the register exposed to compiler to the physical physical reservation station in the processor. So in this way, you are trying to use additional register to avoid the issue of false dependency. So that's why the idea of Tomasulo algorithm would work. And another thing that Tomasulo algorithm try to address is that we mentioned that previously in a pipeline design, saying that if we want to accommodate like integer instruction, memory instruction, multiply instruction, or branch instruction, we turns out have to make a super long pipeline, right? So for example, if we really have if we want to make a single pipeline for 4 different types of instruction, well, the integer and the address resolution could be combined. However, for the floating point multiply and the branch, well, the branch can be combined, but for the multiplication, you probably need an additional stage. So it turns out that every instruction has to go through like 1, 2, 3, 4, 5, 6, 7, 8, 9 stages, right? So you have to make a super deep pipeline. So, and in a lot of cases, those stages are not working at all. So Tomasulo algorithm try to address that by making 4 different pipelines for different instructions with its issue logic to issue the instruction to the right pipeline and then use the right backstage that broadcast the results through CDB. So this broadcasting, if you have ever been to DMV, right, you should have a very a good experience about what that looks like. It's like now serving B16 at window number 26, something like that, right? So this is the CDB. And the window number 26 is like the pipeline that the instruction is assigned to. And the B16 is the instruction that will be called, right? So that's the basic idea of Tomasulo algorithm. So if you look at the hardware of supporting Tomasulo algorithm, basically before the instruction is issued, you need an instruction queue. And associated with the instruction queue, we have reservation stations, and the reservation stations record what's the detail of instruction. So for let's set this memory pipeline aside. Let's look at the integer pipeline that's easier to understand. For the integer pipeline, this would tell you what instruction is in a reservation station. For example, is this an add or is this a subtraction? Or what's the operand one? Like what's the input operand? So the input operand could be a real register or a reservation station name, for example, like integer 3, right? And there are some flags here to tell if there are something that we have to take care of this instruction. And then after its operand is ready, this instruction can go to the integer ALU. And when we finish the operation in integer ALU, we will broadcast our results through the common data bus. And as you can see, the common data bus is connecting to all reservation stations, as well as the register status table, which tells you if I want to find the most up-to-date value of a register, which reservation station should I go to? So that's the basic idea of Tomasulo algorithm. So before the lecture begins, before we have the question, it's always good to know where the standing is. And as you can see, last lecture Valors make a very, very significant progress toward it. But surprisingly, the Mystics, they also get a very good progress. But other teams, you still have the chance to catch up. So today we are going to continue our discussion on Tomasulo algorithm. We are going to talk about register renaming. We are going to talk about superscalar if we have time. We are going to talk about simultaneous multi-threading. So talk about register renaming is, as I said, it's used on this grandfather old computer called IBM 360 model 91, but it's not, it's this computer, you can only see it in the museum or maybe some other places, I don't know. But what really important is that the Tomasulo algorithm and the concept behind it. And this is the processor, as I mentioned, how to support the Tomasulo algorithm. So now let me walk through the Tomasulo example with this 10 instruction sequence so you will get an idea how it works. So to simplify the expression, and actually I know from your end it's not very simplified. So let me explain what's going on here. So this is a combined reservation station, meaning that, and to make an example, I would say to create some of the cases why Tomasulo algorithm is not in use, I specifically changed some of the reservation station we have from the original Tomasulo design in a way that this two, I only reserve 2 integer reservation stations. In addition, we also have like 2 reservation stations for multiplication, 3 reservation stations for low store, and also for this pieces of a code, because we are only using 5 of the registers, so I only have a 5 entry register status table, but in theory, we should have as many as the number of registers we supported. And with each register status table, it will tell you what's the up-to-date reservation station number. That will generate the result. Or if we already have the value in the execution sequence, it would have the value. And the spec means that if the result is trustworthy at this point. So this is Tomasulo in motion. And so now, and for this is also, if we have confirmed the result from somewhere, then we will put the input in this period, in this 3 columns. However, if we have something that's ongoing, we will put the link here. So let's look at that. So the first instruction we are going to deal with is the load instruction. And remember, for the load instruction, and now we assume all the instruction has been decoded. So now the load instruction is going to be in a dispatch stage. And for the dispatch stage is meaning that we are going to find a reservation station for this instruction. And right now, because all the reservation stations are empty, so we can, and because this is a load instruction, so we can comfortably put the load instruction in the first load reservation station. And this is a load instruction, so the instruction is load. And for this instruction, you can see one of the input is 0 as a constant. So we put, and this is a fixed value, so we put into the VJ. And at this point, we assume that the X10 value is not speculative and is determined. So we get the up-to-date X10 value here. And because it's also, so we also put it in VK, because this, for this V columns, they means that the value are already ready. And this instruction is going to generate an output to X6, but this X6 before this instruction is done, there's the value is not determined yet. So we have to update our register status table to warn the upcoming instructions. If you want to get the up-to-date value from X6, reservation station load 1 is where you want to get this instruction. So now we finished the dispatch for the load instruction. In the next cycle, we are trying to dispatch the add instruction. And when we dispatch the add instruction, it's an integer instruction, so we put it into the integer 1 reservation station, and it's an add operation. The X12, again, because right now nobody is modifying it, so it's determined, it's not speculative, so we put it in here. However, for the XC value, another input from the register for this instruction, if you look at the register status table, it says that, well, it comes from reservation station LD1, so you put LD1 here, right? And if it's in a queue, it means that this value is not determined yet, so we cannot issue this instruction until this has been addressed. So, but in the meantime, if you look at the load instruction, because all the values are determined, so there's no reason why we should not let this instruction go to address queue and later on being address resolved. So now the next cycle, we are trying to dispatch the store instruction. And for the store instruction, there's no one other than this instruction would be occupying the reservation station. So safely put it there. And similar to the load instruction, the X10 value is no one is modifying it, no one is changing it, so use it. And this 0 value is also constant. So as you can see, um, this instruction can be safely doing its address queue and address resolution. However, remember, store is a very interesting instruction, is that all of its encoded registers are inputs. So here the X7 is actually an input. But if you look at where can we find the up-to-date X7 is actually integer 1, which is not determined yet, which is not generated yet. So we put a value here. An entry here, notifying that this instruction can only be issued, meaning that you can only do the memory operation until the integer 1 is resolved. So now in the next cycle, again, this is an add I instruction. We try to dispatch it, and there's still another entry in a reservation station, so we put it there. And again, if you look at the X10, nobody is still modifying it. So it's safely you can do this, right? And also for this X10, because for its output is also X10. So previously, there will be an issue if the add I instruction out over executing. However, right now, if you have a table like this telling that, well, for all the following instruction, depending on X10, you should look for the entry in integer 2, which means the reservation in integer 2 to figure out your up-to-date value. Then you can still go through, right? So here you should have some feeling, Tomasulo algorithm is really use a different register to address the false dependency issue for out-order execution. And in the meantime, as you can see, integer 1. So we are still waiting for it, right? So now, in the next cycle, we are going to dispatch the branch instruction. And again, the branch instruction here, it's empty. So we put, we try to fill this reservation station. And for this instruction, it depends on X5 and X10. However, now, if you look at the register status table, the X10 must be waiting for the outcome of integer 2. So instead of putting X10, we have to, we cannot put X10 here. We have to use the result from integer 2. So in this way, you see all the following X10, they are decoupled from the X10 that instruction 1, 2, 3 that are working. They are depending from. So you are decoupling, and remember the tree we have, right? The 1, 2, 3, and 4, they are different trees, right? So with this Tomasulo algorithm, with this renaming, you are actually decoupling these 3 trees. So for 1, 2, 3, they all use the value of X10. However, for following instructions that depending on the X10 generated by 4, they will be using integer 2 instead of X10 in the future. So in this way, you are decoupling these 2 trees of data dependency. Now, and in the meantime, because for the load instruction is not depending on anything, so we have it go to the memory stage. And it's interesting in the next cycle, right? So for the upcoming cycle, we will see that for the second add instruction, because all its values are determined. And so even though it's now in the issue stage, you know the next cycle, this instruction could be executed. So however, in the meantime, right, the first add instruction in integer 1, because it's still waiting on the value of load 1. So it cannot execute at this moment until we receive the value from common data bus. So for this example, you do see that there's out of order execution happening here. The add I is now ahead of add, right? So this also gives you a feeling that, okay, we are really decoupling the execution between instruction 1, 2, 3 and everything after 4, because everything after 4 now can be going ahead of time, ignoring the execution of instruction 1 and 2. And that's because we already changed the value, right? But for this cycle, the load instruction is doing is write back, meaning that it's broadcasting its value. So so now you know that, well, for the first first load instruction, the value the value of LD1 is actually can be used in the next cycle, right? So in the meantime, you are going to filling the integer one, which is depending on the value of x6, notifying that this instruction can be executed in the next cycle. And it's also interesting, at the same time, the second load instruction, or say the second instance of the load instruction, also use x10 and x6 will be dispatched right now. And we do have an entry for it. And this time it's going to be in integer 2. So you have to update your reservation station register status table that, well, for all the following instructions now, the new value in for XC will be in load 2 instead of load 1. So that's how it works in renaming the logic for renaming the register to reservation station in Tomasulo algorithm. And let's keep going on. So you can imagine that in the next cycle, for the first add instruction, we can finally execute it, right? So now the second instruction will be in the integer stage, and for the fourth instruction, it could be in its write back stage. So again, we broadcast there's a new value for integer 2. Everyone can use now. Everyone who is depending on integer 2, obviously this branch instruction can go through now. But in the meantime, we are trying to dispatch the 7th instruction. However, if you look at the number of integer LU reservation stations that we have, there's no free space for it. So we have to wait until we have a free space for this instruction. So now the pipeline will be stalled. So in the next cycle, right, if we broadcast the integer value 2, then this instruction could be activated. And in the meantime, right, the integer 2 could be free up if we put the real value in it, right? So now in the next cycle, what you will see is that, well, the integer 2 will be filled with the value and will be filled with the second add instruction, and the branch instruction is now in execution, right? And in the meantime, you will see that the add-I instruction already finished, and it's before its peer to its other instruction in the other tree, the 2 and 3. Right, so you really see that Tomasulo algorithm is trying to decouple the execution of 1 to 3 and everything after 4 in this way. So if you keep, so for the rest of the execution, I believe you guys can potentially go through, and you will see that this table would keep repeating the same process and trying to finishing these instructions out of order, right? So right now, if you see instruction 163, they finished. However, other instructions like 8 to 7 to 10, they are still in execution, right? So this is really out of order execution, out of order completion, right? So finally, we spend a total of 13 cycles to issue all instructions, right? However, if you remember, you might think, well, this takes more cycles than what we have seen in the pipeline. However, remember this, right? If you want to put all these instructions in a pipeline, you need a 9-stage pipeline stages, and this 10 instruction would definitely cause more stalls because the load and add, and because of the add and stores, right? So this is actually more efficient, and you are executing instruction out of order to fill the gap that your functional units are not in use. So that's the basic idea of Tomasulo algorithm. Okay, so finish talking about Tomasulo algorithm, you feel like, wow, it's a lot, right? And you have to remember what reservation station. And there are cases that the Tomasulo algorithm cannot do well because we are limited by the number of reservation stations that we have associated with each functional unit. So if you look at the paper that I assigned to you, the MIPS R10K and the Alpha 21264 microprocessors, they are actually using a different mechanism called register renaming. And although these are processors, seems like more than 20 years ago, however, all the all modern processors, they are using exactly the same register renaming, well, similar register renaming mechanism that these papers are talking about. So it's more important for us to know what's the real world looks like. So I didn't give you any practice for Tomasulo algorithm, and the reason why I still spend 20 minutes in Tomasulo algorithms because I have been told that if you fail the comprehensive exam for this class, you might have to take the comprehensive exam from other classes. And as far as I know, other instructors for CS203, they still consider Tomasulo algorithm as an important part for CS203. So that's why I still walk through the Tomasulo example for you, and I give you a homework assignment to to practice the Tomasulo algorithm. However, I can tell you that I'm not going to test you for the Tomasulo algorithm in a final for my class because I don't think it's that important anymore. But the reason why I still walk through it is just because I want you to know there is such a thing existing. And well, I'm not going to test you how many cycles we are for Tomasulo pipeline, but I will ask you why register renaming is a better approach over Tomasulo algorithm. So it doesn't mean that I'm not going to test Tomasulo algorithm at all, but I'm just not going to test a detailed walkthrough like you will have in your homework assignment. And that homework assignment is just prepare you in case you fail the comprehensive exam in my class, but you are going to take that comprehensive exam with other instructors. So now let's talk about register renaming. So we talk about Tomasulo algorithm. It takes 13 cycles to issue all instructions, and a reason why it takes 13 cycles is because there is a reservation station stalled for add. So it means that Tomasulo algorithm has a limitation that because it has functional unit dedicated register reservation station. So if your instruction sequence or your hardware design is not in favor the software that you are running, then Tomasulo algorithm could potentially cause stall because of the structural hazard it has. So so let's think about in different ways, right? So one thing I didn't talk about here is that if you remember this pop count example, previously we have been talking about B is better than A, right? And if you look at the instruction sequence that they generated, the B is better than A, not only because it saves the number of branch per 4 iterations, but also if you have a very smart compiler, what a compiler would do is that we could use as many registers as possible to rewrite the output in this way. So if you have a data dependency, it could be rearranged and shifted away, right? So the key thing here is that, and also from the previous Tomasulo example, you also know that if we want to avoid a false dependency, then it's really important that you have to make sure that when you are executing these instructions, those architectural registers, meaning that those registers that your code or your programmer can use could be decoupled from the real register, which means the physical register that you can use. so that you can allocate a new physical register for a new output. And previously in Tomasulo algorithm, the new physical register is a reservation station. So register renaming is essentially an advanced version of Tomasulo algorithm in a way that now we have a universal set general purpose physical register, or say a general purpose reservation stations for all instructions for all functional units without worry about how many reservation stations should be reserved for each functional unit. So if you have saying that if you have 64 total physical registers for your instruction use, every instruction can use these 64 registers to rename its output. So that's the basic idea of register renaming. And similarly, you still have the dispatch renaming stage, which allocate a physical register. And remember previously it's Tomasulo algorithm in its reservation station. You still have the issue, you still have the execute, you still have the write back. So everything is very similar, except in your hardware right now, we have a renaming logic. And what the renaming logic is doing is that we have a mapping between physical registers and the architectural registers that you are using in your code. So saying that in this example, the X1, we have a pointer to P1. So meaning that the current X1, you can find it in P1. So after you rename those instructions, you still have the instruction queue to store the renamed instructions. And when you execute the instructions issue the instruction from the instruction queue is based on if the physical registers have its value resolved. So as you can see, the logic is a lot is different here in a way that the instruction queue is activated by the availability of physical register values. And once a value in the physical register is determined, you can activate an instruction and put it into execution, but the rest of the pipeline is still the same. And when you are done with your execution, those logic from each functional units will be used to notify the physical registers. So that's the basic idea of register renaming processor. So if we want to see what's going on in register renaming, as you can see, we have a renamed instruction queue. We have the physical register table. We have the register mapping table, and we have the mapping between we have a physical registers. And for physical registers is it has the validation bit, it has the real value, and seeing if it's in use, right? So now in the first instruction, as we said, is in a renaming stage. And right now, and this is generating the output to X6. And remember, the policy of register renaming is that whenever you see a new output, you allocate a new physical register for this new output. So now this XC saying that we put X6 in P1. So because the value is not generated yet, so it's valid. And because someone is still is not valid, and because someone is now using it, so you cannot use it anymore. So this register should be preserved. So P1 is using, right? And then because X6 is right now in P1, so this instruction should be rewritten as load P1 X10 0. And now in the next cycle, you know X10 is ready, 0 is ready, right? So this instruction could be put into issue stage and wait for execution. And for the next instruction add, we still rename it. And as you can see, X6 is right now renamed as P1. So you just put XC as P1. And X7 is a new output. So we have to find a new physical register for it. So X7 is now P2, right? So this is the renaming stage. And in the next cycle, because the load instruction is not actually depending on anything, so you can put it into address resolution. And for the add instruction, it's now in its issue stage to check its input. And again, you try to rewrite this store instruction. And don't forget that for X store instruction, all the register inputs, all the registers, they are input. So X7 is actually from P2. And for X10, no one is modifying it and the value is trustworthy. So let's just put X10 here. Now, for the next instruction, add I is outputting to X10, but its input of X10 is determined. So you don't have to rewrite this one, but you have to allocate a new output for X10. And now looks like P3 is a good choice. So X10 will be in P3, and add I will be rewritten as P3, X10, and 8. And in the meantime, the load instruction keep working in keep working on for its progress. And now, for the branch instruction, again, the branch instruction again is depending on X10, and X10 is now in P3, and X5 the value is trustworthy. So you can imagine for the branch instruction, it will be rewritten as P3 X5 loop like this, right? And in the meantime, for the add instruction, like what we happened in the Tomasulo algorithm, because the P1 is still not valid yet, so we cannot have this instruction issued. But in the next cycle, right, you will see that when we are checking the availability of the operands, you will figure out that for the add I instruction, X10 and 8, they are ready, and P3 is simply the output. So in the next cycle, you can put this add I instruction into execution. But in the meantime, the first add instruction has to be waiting for the outcome from the load instruction, which is finally become valid in this cycle, right? So in the next cycle, the add instruction can be put into execution. And but in the meantime, the add I instruction already finishes execution right back its result. So everyone who is depending on P3, like the branch instruction, like this load instruction, can be executed. And previously, remember, for the 7th instruction, we have to wait for a reservation station. But right now, because the physical register is free for you to use, right? So this output of X7, we can actually put it into P5 because there is still available physical register for you to use. So this instruction does not have to stall anymore, and it can be put into its rename stage, and it could be issued in the next cycle, right? So if you keep going, and you will figure out for this pipeline, it only takes about 12 cycles to put all instructions into execution, which avoid the conflict or the structural hazard in reservation station. So that's why register renaming is now more popular, or say it's replacing the Tomasulo algorithm because of its availability to avoid the structural hazard in reservation stations. So now you might feel like, oh, sir, do I have to draw a pipeline like the register renaming every time when you ask me how many cycles it takes to issue all instructions? The answer is no. Let me teach you a better method of figuring out how many cycles it takes to issue all instructions. So for this pipeline, as you can imagine, right now we are completely scheduling instructions depending on if its data hazard or its data dependency has been addressed. So you are completely scheduling instructions based on the availability of its operands after it has been put into issue stage. So it's completely based on your data flow graph in scheduling. So the key thing is that all you need to do is to draw the data flow graph. So saying that, now we are at cycle 1. And for cycle 1, we put one instruction into the instruction queue. So now there's only one instruction in the instruction queue. And the second instruction, the second cycle, we are going to have the second instruction in the instruction queue. And the second instruction is depending on the first instruction. And you remember, if you look at this diagram, right, for this is the register renaming pipeline. If you have an integer instruction depending on the result of a load instruction, you have to wait for 1, 2, 3, 4 cycles to receive your values. So you should just put an arrow like this, right? So 1, 2, 3, 4 cycles later, you are going to get your result, right? So you know at this point it's safe to issue this instruction because it will go through 1, 2, 3, 4 after you issue it, right? So that tells you that for this pieces of these two instructions, this is the time when the data dependency will be addressed. And this is the time that your output is ready. Now, for the store instruction, it's the third cycle you are having a store instruction into your instruction queue, and it's depending on the value of S7, X10. And S10 is already determined, but for X7, it has to wait for the second instruction, and it needs two cycles. So 1, 2, right? 2 cycles to get the result. Now, for the fourth instruction, that's where we are going to get in a fourth cycle. It's not determining on anyone. It's not depending on anyone because the X10 value is not an output of any of this. So at this time, you are very safe to put X4 into execution when the fourth instruction is entering its issue stage. But for the fifth instruction, it's again depending on the output of fourth instruction, and the fourth instruction is an add-I instruction. So again, 2 cycles, right? So so it should be 2 cycles after the fourth instruction. So that's why it's right here, right? Now, the sixth cycle, the sixth instruction is depending on the X10 generated by X4, by fourth instruction. And this is when we get the sixth instruction. And because when we get the sixth instruction, the value of X10 will be ready. So this sixth instruction could be issued right away when it's entering its issue stage. And for the seventh instruction, it's depending on the XC value generated by the sixth instruction. And the sixth instruction is a load instruction. So you will need this many cycles like this. 1, 2, 3, 4 to 1, 2, 1, 2, 3, 4. Yeah, 1, 2, 3, 4 to generate a result, right? So this is the earliest time you can generate the issue, right? Now, you can issue that instruction. And for eighth instruction, again, right? So for ninth instruction, similarly, it's depending on 9, and because the value of X10 is already ready at that moment, so you can issue it right away. And for 10th instruction, depending on the value of 9, so it has to wait for 2 more cycles. And if you count the number of cycles it takes here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. See what a magic. See what a magic. Right? So through data flow graph analysis, you can easily tell how many cycles it takes to put all instructions into execution without drawing a pipeline diagram as I just demonstrated. So now I want you to practice for this question, how many cycles it takes for us to issue all instructions for this linked list code, this linked list code, and this is the linked list code. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so if you look at the current graph, it looks like a lot of you chose C, and it's very like a normal distribution. So why don't you discuss with your friend? And I know it has been a while. This is probably, except for the first lecture, this is probably the only lecture that we start a discussion this late. So why don't we just have a group discussion right now for probably 2 to 3 minutes? All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so look at what after discussion is that a lot of you believe it's 11. So now let's pick a team to share your result with us. Who? Oh, Rocket Team. Dun, 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 dun. Dun, 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 dun. Okay, I have Jonathan. Great.
All right.
What do you think?
Our team agreed on D12 because of a dependency between the load and the branch not equal cycle of X10. So it's going to be one cycle stall per loop.
Okay,
So
so do you mind to walk through the instruction queue with me?
I don't really know how to do that. It's kind of confusing for me, but I'll try. What would be the first step? I guess we start with number 1 with the load.
Right. And because is it depending on anyone right now?
No.
So can we issue it right away?
Yes.
Okay, so put it here, right? How about the second instruction? Is it depending on anyone?
No. And so then we can also issue it right away.
Right away, right? How about the third instruction? Is it depending on anyone?
Yes.
So, and how many cycles do we have to wait?
1. There's branch forwarding, right?
Yeah, but what input is it waiting for?
It's waiting for... Oh, I guess I misread that with X10.
Right. So X10 is also from a load instruction, right? And remember what we previously mentioned? How many cycles?
I do not remember.
Okay, so for this one, right, for the memory instruction, it takes 4 cycles, right? So now we have to wait for, oops, 1, 2, 3. We have to wait for 4 cycles, right, like this, to issue this instruction, right?
Okay, yes, right.
Okay, how about the 4th instruction? Can we issue it right away?
The load? No. Isn't there a dependency
Why?
between 3 and 4 because of the 8, or is that a false dependency?
Is it depending on 4? Well, assume that if we have a perfect branch predictor.
No.
So who is it depending on still?
It's not depending on anything.
Right, so it's depending on the first instruction, right? So you can only issue it, right? So how about the 5th instruction?
No, that's fine. There's no dependency.
So the 5th instruction is fine, right? It could be issued right away, right? How about the 6th instruction?
Wouldn't that technically still be dependent on the first one, but it should be fine by now? No, not the first
Is it
one.
depending on the first one?
Sorry, the previous loop, but I don't think that's right.
Right, so for the 6th instruction, where can we find the X10 we want?
It would be from the 4th instruction.
Right, so we still have to wait for another 4 cycles for that, right?
Yes.
Right, and for the 7th instruction, it's also depending on the 4th instruction. So it can be issued only right here. All right, and for the 8th instruction is not depending on anyone, so it could be issued right away. And for the 9th instruction, again, it's depending on the output of 7th, right?
Right.
But if you look at that, right, for the optimal case, right? Well, for the optimal case, even though we have the capability of issue all these instructions, well, even though we have the capability of issue all these instructions right away, right? Whenever we need to issue that, right? It takes about I hate this animation. Okay, it takes about, okay, sorry about that. 1, 2, 3, 4, 9, right? It takes about 10, 11, 12, 13 cycles at least to issue all instructions, right? So.
Okay, so it wasn't 12, it was 13.
So it's 13 at least, right, for this example. All right, but thanks a lot for Jonathan, and thanks for walking through this example with me. So now you should know, wow, computer scientist, you love linked lists. You thought it's a good idea. However, for this instruction, their performance is terrible. In a lot of cases, we cannot find an instruction to issue, right? So now, and if you don't trust me, and if you try to draw the pipeline diagram, you will figure out they will spend 13 cycles to issue as what I draw here. Okay, so what? So we just talked about that. Well, we have a pipeline processor that can fetch an instruction, issue one instruction at a time. However, if you look at the pipeline we have, we are actually having more than one functional unit at a time, right? So, and if you only can issue one instruction at a time, there are chances that these functional units, they will be wasted. So our idea is that, okay, if we are able to fetch more instruction, decode more instruction, rename more instruction, and potentially issue more instruction at the same time, we are going to fully utilize all the pipelines that we have. So this idea is called Superscalar. So so the idea of Superscalar is not too different from you will have similar pipeline similar number of functional units. However, we improve the front end of this processor in a way that we widen the fetch, decode, and issue logic to accommodate more than one instruction at the same time. And so now the processor has two things that you have to care about. One thing is the fetch width, meaning that the front end, meaning the fetch, decode, and issue, the capability of how many instructions can the processor fetch and decode for each cycle. And the back end, regarding how many instructions can the processor issue, meaning that put the instruction into execution in each cycle. So in this pipeline, you can imagine in a Superscalar processor, from what the program would see is the fetch width. However, after you decode it, rename each instruction, the capability of the processor is completely depending on how many pipelines that you have in the processor. So that's the backend part. So you can also imagine one thing. If we have a processor that can do decode, that can do rename, and potentially rewrite your assembly language, the capability of your processor is completely depending on the backend of your microprocessor architecture. So saying that if I have an instruction, no matter what instruction that I'm using, what instruction set I'm using, as long as my front end can fully utilize the back end of my processor, their performance is supposed to be similar. So in this way, you can see modern processor design, they actually decouple the front end, which is instruction set architecture dependent, through with its backend, which is more microarchitectural dependent. All right, so that's the Superscalar design that almost every processor is using. So the Superscalar processor is simply an extension of register renaming processor that we just widen the register renaming processor. So assume that we have a 2-issue register renaming processor. What would happen is that we, in a same cycle, we fetch and rename 2 instructions, and we can put this 2 instruction into issue stage. And whenever an instruction is ready to execution, we just issue that instruction. And in the meantime, if we found 2 instructions that could be issued at the same time, we just put them into execution. And so in this way, you will see like this pipeline, they are better utilized in a way that there are more than one instruction executing at the same time in a pipeline, like this integer and a branch they are using at the same time, which is not happening in the past. So if you have a 2-issue register renaming pipeline, you will figure out for this pieces of instruction, it takes only 2 cycles to issue all instructions at all. So if you want to use the same approach that so you can still use the same approach by extending the data flow graph mechanism that we use to evaluate. So right now, I just want you to try how can you extend the idea of data flow graph analysis on the linked list code again for this question? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now, according to your vote, it looks like we definitely need some discussion. So why don't you go ahead and have discussion real quick? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to your result, it looks like, well, two answers are quite popular, B and E, but I do want a group to tell me, what do you guys think? So which is the group? Okay, Mystics, it's your show time. Okay, so Chi Chu,
Yes.
are you from
We-
Mystics? Yes,
Yes.
you are. Okay.
Okay. We thinking is B for 10 because the load
Uh-huh.
and add-I instruction can be both fetch at the same time. So that's basically we're receiving one
So we can
cycle and
fetch two at the same time.
yes,
So in the first cycle, we can issue 1 and 2, right?
yes. And
But
then
how about the next cycle?
the branch not equal will have to still store for that case. So
Uh-huh.
trying to fetch 4 will have to still wait for it.
Uh-huh.
And then after that
5
we
and
can
6.
store 5 and 6 and 5 can continue, but
5
then
can
6,
continue.
yes, 5 can
Well,
continue and
6.
6 have to be also stored for another 4 cycle for that until it
Uh-huh.
get the result from extend.
So next
And then
cycle, we got 7 and 8.
7 and 8 and 7 can be starting and 8 can also be starting, but then for
7
the
can start. Can 7 start?
wait 7
7 is waiting for
7 is low extend and oh wait, I think I may be a bit confused on that.
Okay, so for the 7, which instruction would generate the X10 we want?
From the instruction 4.
Right. And when the value of instruction 4 will be ready.
4 cycle after it.
Right. Okay. So for 8.
Oh, I
Can we
thought
go?
after 6, like after 6 and 7 came together, sorry.
Right.
Okay.
So 6 can be executed immediately, right? So how about the 9th?
The 9th have to wait for the result for 7. So basically 4 4 cycle after 7.
Right. So for this linked list, how many cycles do we still have to wait?
Oh,
Is it 10?
1, 2, 3, 13. More than 13?
Yeah, again, 13.
Ah, okay. Makes sense.
Right. But thanks for walking through, right? So it looks like you guys didn't really draw the data dependency graph. And I understand it's difficult because the limitation of Zoom, right? You cannot, I don't know, I don't think you guys can share your screen in the group discussion. So I know it's a limitation, verbal discussion, but it looks like you do understand the concept, right? So if you carefully draw the data flow graph, you will figure out, gosh, for linked list, even though I give you a better processor, it still takes the same amount of time to execute. Okay, Superscalar doesn't help for linked list. Unfortunately, right? It still takes about 13 cycles, right? So that is a disaster, right? So if you are a good software programmer, now you know what kind of code that you shouldn't use when you are trying to optimize your code. Like linked list, it doesn't work well, because if you look at the linked list, you will figure out that in a lot of cases we are wasting the capability of your processor in issue instructions, and the instruction level parallelism is very low because you have data dependencies like that. So if you generate code with low data dependencies, right, then the performance of that code would not be great. So in the next lecture, we are going to talk about other architectural optimization to better utilize your processor for this instruction level parallelism. And in addition, you might be aware that, well, this out of order execution has its own drawback in a way that, what if I have branch mispredicted? What if, and you will figure out that if six instruction is mispredicted, saying that the linked list finally met a null, right? 6 instruction will not be, the 7, 8, 9, and 8, 7, 8, 9, they shouldn't be executed. However, because of out of order execution, we may already be finishing executing 8, right? So that's definitely not going to give you the right result. So in the next lecture, we are going to talk about the architectural optimization to accommodate branch misprediction, exceptions, and try to fully utilize your hardware. So don't miss the next lecture. I know it's the Monday after Thanksgiving. It's also another difficult day for you to attend a lecture, but it's important. And in the meantime, before you leave the classroom, before you go for your turkey, before you go to meet your family or the funeral service of a turkey or whatever where you want to go, or you want to stay at home like me, there are a few things I want to let you know. First of all, the project is already there. Check the website and start it early. And I'm not going to extend the due date. And assignment 4 is up. Also start early. Office hour for Zoom is on Zoom. I don't think the TA is hosting one this Friday. So for this week, if you really need someone to talk to, I am the only one today at 2 p.m. And again, check your weighted total in iLearn so that you have a better idea where your standing is. Other than that, enjoy your Thanksgiving holiday, and I will see you next week.